Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're working examples that illustrate basic concepts of stress and strain. The next example is based on an illustration that is from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. This is a rigid beam that's pin connected at point C, and the beam can rotate about that pin. In addition, at the ends, it's connected to two axial bar members, member 1 and member 2. This problem is actually indeterminate, so it can't be solved from basic principles of equilibrium alone. However, we're given that under the loading P, and we don't know what P is, but we're given that point B, that's right here, it moves downward 3 millimeters after the load is applied. And we're asked to evaluate the normal strain in bars 1 and 2. So this is a basic geometry of deformation problem or compatibility problem where we need to consider how the mechanism moves and relate the deformations in these bars to the downward movement. Okay? So as I mentioned before, we pull down here, the whole bar is going to rotate about the pin at C. And this distance right here, I'll call that delta B, is given as 3 millimeters. This distance right here, bar 1 is going to move down or elongate. I'm going to call that delta 1. Bar 2 over here is going to move upward. The bar is also elongating. We'll call that delta 2. And we want to find the normal strains in bars 1 and 2, which we use the symbol epsilon for normal strain. So find epsilon 1 and epsilon 2, and recall that the definition for strain epsilon is equal to a delta, or a change in length or elongation, divided by the length of the member. So in order to find these strains, we'll start by finding the deformations, and we'll do that using the geometry of deformation. I'm going to draw another sketch, which you should always do when you solve your problems. So there's my original bar here, okay, and it's going to rotate about pin C. This distance over here, delta 2, let me insert all the lengths, 650 millimeters. Okay, downward movement here, delta B is equal to 3 millimeters. This length right here is 480 millimeters. And finally, this distance or downward movement there, I'll call that delta 1. And this entire length here, 1150 millimeters. Okay, so hopefully you recognize that we can use similar triangles to relate the deflections, and I'll start with delta 1. Remember, delta B is known, and so I can say that I can say that I'll start with a larger triangle. Delta 1 divided by 1150 is equal to the ratio of lengths on the smaller triangle, delta B divided by 480. And these are all lengths, so I just went ahead and dropped the units. So let me solve for delta 1 here. Delta 1 is equal to delta B, which is 3 millimeters, times 1150 divided by 480. That gives me, when I calculate it out, 7.19 millimeters. So I'll do the same thing for this deformation or elongation delta 2. Here's the ratio of this lengths on this triangle. They're the same as for this triangle, so I can say delta 2 over 650 is equal to delta B over 480. Therefore, delta 2 equals delta B, 3 millimeters, times 650 divided by 480, which equals 4.06 or 4.06 millimeters. Okay, now the next step is to convert those deflections or elongations into strain. So let's start out and calculate epsilon 1. Epsilon 1 equals delta 1 over L1 equals 7.19 millimeters. And then the important thing here is the value for L1. And a lot of students will kind of get confused when they see these assemblages. Remember, we're calculating strain in bar 1, so we need the length of bar 1, which is 2250 millimeters. Okay, and that value computes to 3.19 times 10 to the minus 3, and it's unitless, and that's an acceptable form of the answer. Your textbook also likes to use convert strains to what is called microstrain, which is equal to 10 to the minus 6 strain. So if we wanted to convert to microstrain, we'd multiply this by 1,000, and then we have 3190 microstrains. So either one of those is an acceptable answer for the strain in bar 1. Okay. Strain in bar 2, epsilon 2 equals delta 2 over L2. That's going to be 4.06 millimeters divided by the length of bar 2, which is 1600 millimeters. And that is equal to 2.54 times 10 to the minus 3, or 2540 microstrains. Either of those is an acceptable answer. Okay. Sanity check. Strains are small values. Those are small values. I can check kind of the numbers based on geometry of deformation. Delta 1 is larger than delta B, and delta 2 is a little larger than delta B, so I feel fairly comfortable with those numbers. And that concludes this example.